Hello everyone. Voyager's solar system scan. What it found and what it's still finding. Tonight, we're going to follow two travelers. They are not astronauts. They don't carry a camera crew. They don't speak in words. They speak in faint radio tones, timed pulses, and streams of numbers. Voyager 1 and Voyager 2. Launched in 1977, when computers were large and slow, when a phone call crossed wires instead of space, when the outer solar system was still mostly a set of blurred hints. Voyager's original mission was bold but straightforward. Visit the giant planets, take pictures, measure fields and particles, and then, if the spacecraft survived, keep going. And they did survive. They kept going through Jupiter and Saturn. Voyager 2 continued onward to Uranus and Neptune, the only spacecraft ever to visit those worlds up close. And then both of them kept going still, leaving behind the bright planets and heading toward the dark frontier where the sun's wind finally loses its grip. So when you ask, while Voyager scanned the solar system, what did it find? What were its latest detections? The real answer is a long, gentle timeline. Some discoveries were sudden and cinematic. Volcanoes on a moon, rings where no one expected them, storms that looked alive. Other discoveries were quiet and technical. The sound of plasma beyond the Heliopause, the behavior of magnetic fields at the edge of the sun's influence, the slow change in cosmic rays as the spacecraft moved into another environment. Tonight, we'll walk through both. We'll start with what Voyager found at the planets, because that's the part that feels like exploring. Then we'll drift outward to the invisible solar system, the Heliosphere, the sun's bubble in space. And finally, we'll talk about what Voyager is finding now in the most recent phase of its journey. Not new planets, but a new medium. Interstellar space. Take a slow breath. Imagine the sun not just as a glowing star, but as a source of wind particles flowing outward in all directions. Imagine that wind shaping a vast, protective bubble around our planetary system. And imagine two tiny machines still moving, still measuring, still whispering back. Let's begin where the light is strong. Jupiter, the planetary discoveries, what Voyager found while crossing the outer solar system. Voyager didn't scan the solar system like a radar dish sweeping a map. It scanned by passing through places we had never been, taking close-up measurements in real time, and at each major planet, it changed what we thought normal looked like. Jupiter, a kingdom of storms, radiation, and surprising moons. When Voyager reached Jupiter, it entered a realm where magnetism dominates. Jupiter's magnetic field is enormous, so strong and so extended that it creates a vast magnetosphere, a space environment of trapped particles, intense radiation, and complex plasma dynamics. Voyager helped map this system in detail. It showed a magnetosphere that behaves like a rotating engine, sweeping charged particles around with the planet's rapid spin. Auroras driven not only by solar wind, but also by material coming from Jupiter's moons. A radiation environment so intense that it immediately became a defining engineering challenge for future missions. But the most famous Jovian discovery wasn't a field line or a particle spectrum. It was a volcano. Voyager revealed active volcanism on Io, Jupiter's innermost large moon, not ancient, frozen evidence of eruptions, not vague hints, active plumes and fresh-looking flows geology happening right now. This was a turning point. Before Io, active geology outside Earth felt rare and exceptional. After Io, the solar system became a place where internal heat, tidal forces, and chemistry could drive constant change. Voyager also helped sharpen our understanding of Jupiter's atmosphere, bands, storms, and the complex layering of clouds. The Great Red Spot was already known, but Voyager helped place it in a broader context. A planet where storm systems can be long-lived, where energy flows are enormous, and where weather can be an organizing principle of an entire world. And then, almost like a quiet footnote that later became a major theme, Voyager found that Jupiter has a faint ring system. It's not like Saturn's rings. It's subtle, dusty, and hard to see. But it matters, because it told us something simple and deep. Rings are not rare. They can exist as delicate structures, maintained by small moons and continuous replenishment. From Jupiter, Voyager moved toward the planet most associated with rings, Saturn. Saturn, rings, moons, and the complexity of a world system. Saturn is a planet that looks serene from afar. But Voyager showed that Saturn is not just a planet with rings. It's a complex system of interacting components: rings, moons, plasma, magnetic fields, and atmosphere. Voyager helped reveal fine structure in Saturn's rings, including gaps, waves, and patterns shaped by gravitational resonances. Shepherd moons, whose gravity helps sculpt ring edges and maintain sharp features. Dynamic ring behavior, not a static disk, but a living structure responding to countless small influences. Voyager also studied Saturn's moons, and one moon in particular reshaped planetary science: Titan. Voyager found Titan's atmosphere to be thick and rich in nitrogen, with a haze that obscured the surface in visible light. Titan became a world of chemistry, where sunlight and particles can drive the formation of complex organic molecules in the upper atmosphere, a place that feels, in a distant way, like a laboratory for prebiotic processes. Voyager's flyby couldn't see Titan's surface clearly, but it established Titan as a major target for future exploration, and decades later, missions like Cassini and Huygens would build on that foundation. After Saturn, the paths split. Voyager 1 took a trajectory designed to reach Titan and then head upward out of the plane of the planets. Voyager 2 continued in a line that would carry it to Uranus and Neptune. So now, in our story, Voyager becomes two stories. One traveler leaves the main highway early, heading for the borderlands. The other keeps going, toward planets that had never been visited at all. Uranus, a sideways planet, a magnetic mystery, and new moons. Uranus is famous for its tilt. It rotates on its side, as if something long ago knocked it over. Voyager 2's encounter revealed a world that felt like a set of surprises arranged carefully in the dark. Voyager 2 found a magnetic field oddly tilted and offset from the planet's center, suggesting a dynamo process unlike Earth's. A cold, pale atmosphere with subtle cloud features, more complex than earlier telescopes had shown. New rings and ring structure, again reinforcing that rings are not exclusive to Saturn. New moons and detailed images of known moons, showing diverse surfaces shaped by impacts, fractures, and on some signs of internal processes. Uranus's magnetosphere in particular was strange. Because the magnetic axis is tilted, Uranus's magnetosphere changes dramatically as the planet rotates, creating a space environment that wobbles in a way that challenges simple models. Voyager's data turned Uranus from a distant cyan dot into a world system with its own rules. And then Voyager 2 went on to Neptune. Neptune, fast winds, a dark storm, and a moon that breathed geysers. Neptune is far enough that sunlight is weak only a small fraction of what Earth receives. Before Voyager, many scientists expected Neptune to be quiet and cold, perhaps sluggish. Voyager found the opposite. Neptune had remarkably fast winds, some of the fastest measured in the solar system. It displayed large storm systems, including the famous Great Dark Spot, a feature that made Neptune feel suddenly like a living weather machine. Voyager also revealed Neptune's rings faint, dark, and surprisingly clumpy. Not smooth, not evenly distributed, but structured as if the ring material gathered into arcs, held in place by gravitational effects and subtle resonances. And then there was Triton. Triton is Neptune's largest moon, and it orbits backward relative to Neptune's rotation, a major clue that Triton may have been captured long ago. Voyager found Triton to be astonishingly active. It observed plumes, geyser-like eruptions, likely driven by sunlight heating nitrogen ice and causing seasonal pressure changes. In the dim outer solar system, where you might expect frozen stillness, Triton showed motion, breath, geology powered by subtle energy. This was another theme Voyager planted deep in our thinking. Even far from the sun, worlds can be active. Not necessarily with volcanoes of molten rock, but with ices, chemistry, and seasonal physics that create real change. And with Neptune, Voyager 2 finished the grand tour. No other mission has repeated it. No spacecraft has visited Uranus and Neptune since. Voyager's planetary discoveries remain a backbone of outer planet science. But Voyager didn't end there, because after the planets, the solar system does not simply stop. It becomes something else, a vast, invisible structure shaped by the sun's wind. And this is where Voyager's most recent findings live. In the Heliosphere, the solar system's invisible border. What Voyager found about the Heliosphere. To understand Voyager's later discoveries, we need to reframe the solar system, not as a set of planets, but as a bubble. The sun constantly emits a stream of particles called the solar wind, mostly electrons and protons flowing outward at hundreds of kilometers per second. This wind carries the sun's magnetic field with it, forming the heliospheric magnetic field. As the solar wind expands, it becomes thinner. Far from the Sun, it begins to slow as it encounters the interstellar medium, the thin gas and magnetic field between stars. So the heliosphere is shaped by a pressure balance: outward pressure from the solar wind, inward pressure from the interstellar environment. This creates boundary regions with names that sound almost like geography. The termination shock, where the solar wind slows from supersonic to subsonic. The heliosheath, a turbulent region of slowed solar wind beyond the shock. And the heliopause, the outer boundary, where solar wind influence gives way to interstellar space. Voyager was never originally designed as a heliosphere boundary mission, but it became one because it kept flying. The termination shock, the first major edge. Voyager 1 and Voyager 2 both crossed the termination shock at different distances and times because the heliosphere is not perfectly symmetric. It breathes with solar activity and responds to variations in the interstellar medium. Crossing the termination shock was like moving from a steady wind into rough water. The particle environment changed. The behavior of fields changed. The solar wind's speed and properties shifted. This was our first in situ confirmation that the solar wind undergoes a major transition far from the Sunday. The heliosheath, a turbulent buffer zone. Beyond the termination shock lies the heliosheath, often described as a region of slowed, compressed solar wind plasma, mixed and churned by turbulence and large-scale structures. If the inner solar system is a calm river near its source, the heliosheath is like a delta full of eddies and shifting channels. Voyager measurements in the heliosheath helped reveal variability in plasma and energetic particles. The behavior of magnetic fields in a region not dominated by any planet, the way cosmic rays are modulated, suppressed, or filtered by the sun's bubble. And then came a milestone that sounds simple but is profound. Voyager 1 crossed the Heliopause and entered interstellar space in 2012. Voyager 2 followed in 2018. The solar system, in the heliospheric sense, finally had an edge measured from the inside. Interstellar space, what Voyager found after leaving the sun's bubble. Crossing the Heliopause is not like crossing a wall. There is no sign that says, "Now leaving the solar system." It is a transition in the dominant environment, a shift in particle populations, magnetic field behavior, plasma density, and the direction of influence. The key idea is this: inside the Heliopause, the solar wind dominates. Outside, the interstellar medium dominates. And Voyager provided multiple lines of evidence that the crossing happened. The cosmic ray switch: more galactic particles, fewer solar particles. One of the clearest signs of Voyager 1's Heliopause crossing was a dramatic change in energetic particle populations. Solar origin particles dropped. Galactic cosmic rays increased. Cosmic rays are high-energy particles arriving from outside the solar system, accelerated by supernova remnants and other energetic astrophysical processes. Inside the heliosphere, the solar wind and its magnetic field help shield the inner regions, reducing the cosmic ray intensity. But beyond the Heliopause, that shielding fades, and cosmic rays become more abundant. Voyager measured that change directly. It was like stepping out from under an umbrella into a light rain of energetic particles. Not dangerous at Voyager's location in any practical sense for a machine, but scientifically unmistakable. The magnetic field, continuity, and surprise. 8. Voyager also measured changes in the magnetic field. Scientists expected the heliopause might show a sharp change in magnetic field direction, like crossing between two distinct domains. What Voyager found was subtler. The magnetic field strength changed, and the environment changed, but the field direction did not rotate as dramatically as some models expected. This led to ongoing refinement of heliosphere models. The heliopause may be shaped and draped by interstellar magnetic fields in complex ways, producing a transition that is real but not always geometrically simple. This is one of Voyager's gifts to science. Not just confirmation, but constraint. Reality is often more intricate than our clean diagrams. The sound of plasma, measuring interstellar density with waves. One of the most poetic Voyager discoveries beyond the heliopause involves something like sound, not sound in air, but oscillations in plasma. Voyager can detect plasma waves, electromagnetic oscillations caused when disturbances move through ionized gas. By measuring plasma wave frequencies, scientists can infer the electron density of the medium. Beyond the heliopause, Voyager detected plasma wave events that allowed researchers to estimate the density of the local interstellar medium. This was important because interstellar space is not empty. It has a measurable density, a measurable magnetic field, and structure. Voyager's plasma wave measurements gave us a direct sense of what kind of material the solar system is moving through. Not thick, not like a cloud, but not nothing. A thin sea of charged particles with ripples and changing conditions. And this connects directly to your question about the latest detections. Because in recent years, Voyager's ongoing measurements have continued to refine interstellar plasma density estimates, the variability of the interstellar magnetic field, the behavior of cosmic rays with distance, the nature of disturbances propagating outward from the Sun even after the heliopause crossing. In other words, Voyager still detects the Sun's weather, but now as distant waves traveling into another ocean. The latest Voyager findings, recent years, what it's measuring now. Voyager's latest findings aren't new planets. They're a set of continuing measurements at the boundary between star and galaxy, because even now, the Sun is still sending signals outward. Solar eruptions launch shock waves and pressure fronts. These travel through the heliosphere, cross the heliopause, and continue into interstellar space. Voyager can detect their effects as changes in plasma wave activity and particle behavior. Below is a clear, accurate way to describe what Voyager has been finding recently, without inventing a single dramatic claim that isn't supported. Continued measurements of interstellar plasma density. As Voyager moves farther from the heliopause, it continues to sample the local interstellar medium. Plasma wave detections have provided ongoing ways to infer electron density in the region Voyager is traveling through. A broad, consistent theme has been that the interstellar environment is not uniform. Density can vary. Disturbances pass through, and the measurements help map a local neighborhood of interstellar space that we otherwise could only model from afar. The interstellar magnetic field and how it changes with distance. Voyager continues to measure magnetic field strength and orientation. This matters for understanding how interstellar magnetic fields drape around the heliosphere, how cosmic rays propagate, how the heliosphere interacts with the surrounding medium. The story here is not that Voyager found a new magnetic field. It's that Voyager continues to refine how we understand the boundary region's geometry and variability, using direct in situ data. Cosmic rays, the galaxy's particles, now less filtered. Beyond the Heliopause, Voyager measures cosmic ray intensities that are closer to the true local interstellar values. It can still detect changes caused by shocks and disturbances arriving from the Sun, but the baseline environment is more interstellar than heliospheric. These measurements help scientists improve models of cosmic ray modulation, understand the protective role of the heliosphere, calibrate what interstellar cosmic ray levels look like in our neighborhood. This has practical implications for future deep space travel and human missions beyond the protective bubble, even if that future is far off. A dynamic boundary, the heliosphere breathes, and Voyager catches the ripples. The heliosphere is not a rigid bubble. It changes size and structure with solar activity. The Sun has cycles. Solar wind pressure rises and falls. Large solar events, coronal mass ejections, strong solar wind streams propagate outward as pressure waves. Even after Voyager crossed into interstellar space, those waves can pass by, and Voyager can detect them. This means that the solar system, in the heliospheric sense, is not a static object. It is more like a living boundary, a shifting coastline between one medium and another. Voyager's latest detections are, in many cases, detections of that shifting coastline's consequences, measured from beyond it. Engineering updates that matter scientifically, keeping instruments alive. Voyager's modern era includes another kind of latest story: survival. The spacecraft are powered by radioisotope thermoelectric generators whose output slowly declines. To keep the mission going, engineers sometimes power down instruments or heaters, balancing the need to conserve power with the desire to keep key measurements flowing. These decisions shape what Voyager can measure year by year. And even this is part of the scientific narrative, because it reminds us Voyager is not a perfect, fully equipped laboratory. It is an aging traveler, still sending home whispers, and we are learning how to listen carefully with fewer tools. Communications and recovery. Voyager is still talking, sometimes with difficulty. In recent years, Voyager 1 experienced a serious communications anomaly where the spacecraft remained in contact but returned unusable or confusing telemetry, followed by recovery work that restored useful data. This is not a discovery about the solar system, but it is part of the mission's living timeline. And it's deeply human. The spacecraft is far away. Light takes many hours to travel one way. Every instruction is delayed. Troubleshooting becomes an exercise in patience and inference. And when data returns, it feels like hearing from a friend across an ocean. Voyager's latest phase is as much about endurance as it is about measurement. And the measurements, it still returns magnetic fields, particles, plasma wave signatures when available, continue to refine our picture of the sun's environment and the local interstellar medium. What Voyager found about the solar system that we often forget. When people list Voyager discoveries, they often focus on the big planetary moments: Io volcanoes, Triton geysers, Neptune winds. But Voyager also discovered something else about the solar system, something conceptual. The solar system is bigger than the planets. The solar system is not only the region where planets orbit, it includes the sun's vast influence through the solar wind and magnetic field. Voyager transformed the heliosphere from a theoretical structure into a measured place with boundaries, layers, and dynamic behavior. The outer planets are not quiet leftovers. Voyager showed that the outer solar system is not a museum of frozen worlds. It is full of activity: tidal heating, cryovolcanism, seasonal jets and plumes, dynamic atmospheres and storms, complex magnetospheres. The energy sources differ from Earth's, but change is everywhere. Rings are common, and gravity sculpts with elegance. Jupiter has rings. Uranus has rings. Neptune has rings. Saturn's rings are only the most dramatic example. Voyager helped demonstrate that rings can be dusty, faint, clumpy, and shaped by subtle gravitational resonances. It's a reminder that in space, the smallest forces acting over long times can create intricate structure. A gentle catalog of Voyager's biggest solar system discoveries. To help your audience, here's a clean list you can narrate slowly, like turning pages in a book. At Jupiter, Voyager found and confirmed active volcanism on Io, Jupiter's faint ring system. Detailed views of storm systems and atmospheric banding. A deeper map of Jupiter's intense magnetosphere. At Saturn, Voyager found and refined fine-scale structure in the rings, including waves and gaps shaped by moons. Stronger evidence for complex ring-moon interactions. Key measurements of Titan's thick atmosphere and haze. More detail on Saturn's magnetospheric environment. At Uranus, Voyager 2 revealed a strangely oriented and offset magnetic field. New details in rings and their structure. New moons and improved views of known moons. A planet whose rotation and magnetosphere create unusual dynamics. At Neptune, Voyager 2 discovered and documented very fast winds and active atmospheric storms. The Great Dark Spot at the time as a major weather feature. Rings that appear clumpy and arc-like rather than smooth. Triton's active plumes and an unexpectedly dynamic surface beyond the planets Voyager established. The existence and location, in broad terms, of the termination shock. The nature of the heliosheath as a turbulent buffer, the crossing of the Heliopause into interstellar space. Direct measurements of cosmic ray changes, magnetic fields, and plasma density beyond the sun's bubble. That's an extraordinary list for any mission. And Voyager did it with 1970s technology and a stubborn refusal to stop. What scanning the solar system means in Voyager's outer region, it helps to say this clearly, because it makes the script feel grounded and trustworthy. Voyager's modern scanning is not like taking pictures of planets. It is scanning by measuring environmental conditions, magnetic field strength and direction, energetic particle counts and energies, plasma wave activity that hints at density, the presence and behavior of shocks and pressure fronts. These are the senses Voyager still has, like a traveler feeling the wind change and noticing the salt in the air. The planets were landmarks. The Heliopause is a shoreline. Now Voyager is measuring the open ocean. Time, distance, and the soft reality of Voyager's perspective. Voyager is so far away that even simple facts become soothing to contemplate. A command from Earth takes many hours to arrive. A response takes many more hours to come back. Voyager operates with a kind of delayed conversation. Engineers and scientists must predict, must wait, must interpret. Voyager's instruments are not fresh and perfect. They are old but resilient. Some have been turned off to save power. Some still work. And yet, the mission continues because the environment it is measuring is unique. No other spacecraft has gone this far with this combination of instruments. So, each new measurement is valuable, not because it is flashy, but because it is rare. What Voyager's latest measurements suggest about our place in the galaxy? If you want a calm philosophical layer, perfect for a sleep channel, Voyager offers one naturally. The Heliosphere is a kind of cosmic shelter, not a perfect shield, but a meaningful one. It reduces cosmic ray intensity. It shapes the inflow of interstellar particles. It creates a region where the sun's influence defines the space environment. And Voyager shows that this shelter has an edge, a boundary, a place where the solar wind yields. That boundary is not a wall. It is a negotiation. A balance of pressures, a dynamic surface that shifts with time. When you say Voyager found the edge of the solar system, what you mean scientifically is Voyager found where the sun's wind stops being the dominant medium. And beyond that, it found a region that is still part of our galaxy's local texture. A thin plasma threaded with magnetic fields, full of cosmic rays. So the solar system is not an island surrounded by nothing. It is an eddy in a larger sea. A sleep-friendly closing, two travelers still listening. And now, at the end of our gentle tour, we return to the travelers themselves. Voyager 1 and Voyager 2 are not heading toward a particular star. The distances between stars are too vast for that kind of direct voyage. They are simply moving outward, carrying with them the record of what they passed. Jupiter's volcanic moon, Saturn's ring shadows, Uranus's tilted magnetism, Neptune's fast winds and Triton's cold geysers. Then the invisible geography, the termination shock, the heliosheath, the heliopause, and now interstellar space, where the sun's influence is still felt as a distant memory, waves that arrive after long travel, disturbances that soften with distance, cosmic rays that grow more steady, magnetic fields that belong more to the galaxy than to the Sunday. Voyager's latest detections are quiet ones. A slight change in particle counts, a pattern in the magnetic field, a plasma wave signature that hints at density, a subtle response to a shock that left the sun months or years earlier. And yet, these quiet detections are the kind that complete a map, the kind that turns speculation into measurement, the kind that, over time, tell us what it means to live inside a star's bubble. So tonight, as you rest, imagine the heliosphere like a lantern glow in a dark field, bright near the center, fading toward the edges, and beyond it, the galaxy's own night air. Two small machines drift through that darkness, still sending whispers back to the warm world that launched them. The solar system doesn't end with Neptune. Voyager proved that. It continues as wind, as magnetic field, as a boundary, and then as the larger space beyond. And Voyager, even now, is still scanning one faint measurement at a time. Sweet dreams.